Hey dudes, today we're going to do the acid catalyzed hydrolysis of a nitrile. So we have a methyl nitrile molecule right here. This C triple bond N is a polar bond, which gives the nitrogen a lot of electron density, and it also has a lone pair. So if we have acid in the environment, in this case a hydronium ion, we can take a proton from that, and that will lead us into a resonance form.
And in this resonance form, we can move this electron pair to the N, causing the positive to go to the C, and that will make it more electrophilic.
And then we form water as a side product for the first part of the reaction.
Okay, so we are choosing one of these resonance forms for our next step. We're choosing this one because it has less electron density around the carbon atom, so which is more convenient for our second step.
So this carbon is more electrophilic, which means that a water molecule, like the one that we created in the earlier part of the reaction, which has another lone pair, has a high region of electron density around the oxygen, and it can go ahead and attack that electrophilic carbon in our resonance form.
Okay, in step 3, we have formed an amine intermediate.
So water or the conjugate base will take the H or hydrogen to quench the positive charge on oxygen.
And then as a side product, we have the hydronium ion.
Okay. So in this next step, we now have essentially what is a tautomer of an amide, and we need to protonate it in order to get an amide, which is a C double bond O, and then the amine group on one end. So we choose to protonate the N because if we chose to protonate the O, what essentially would happen is the reaction would run backwards. You would get water as a leaving group, and then you could just reform the nitrile that you had at the beginning.
And here we can see the nitrogen takes the H from the hydronium ion, and our side product is water.
So this is a tautomerization of amide, and oxygen will donate its lone pair to the carbon to make double bond, and this bonding pair will go on to the nitrogen to make it neutral.
So now we have an amide tautomer that we tautomerized in the last step. So we can have water attack this electrophilic carbon of the carbonyl. There's a positive charge in the oxygen, so it wants to take electrons and quench this positive charge. This will form a tetrahedral intermediate, like so. And this tetrahedral intermediate has water on it, it has an amine group, it has the methyl that we've always had, and it has a quenched alcohol on it. Now, I'm drawing these as one step, but essentially we have proton transfer, so this will grab a proton from the media, acidic media, and water will form a hydronium from the water that's already on the molecule to quench that positive charge.
Okay, so in step 8, we have the collapse of the carbonyl. Here we have formed ammonium, and we'll take this bonding pair and give it to the nitrogen, thus making it neutral. And then we'll take this lone pair of electrons, giving it here, which will make a carbonyl.
So this is ammonium formation. In this step, we have protonated acetic acid, and we have ammonia in the solution. So ammonia will deprotonate the carbonyl, and we will form acetic acid and ammonium ion.
So if we were to do this reaction in base, I'm not going to go over the whole thing, but essentially you would have a very nucleophilic hydroxide ion instead of water, so you wouldn't need to protonate the nitrile to get a good enough nucleophile that could attack an electrophilic carbon, because you already have a good enough nucleophile that the carbon doesn't need to be made more electrophilic. So you'd have that hydroxide attack. You would need to protonate the imine with water in the media, for instance, and eventually form NH2. And you would end up with ammonia in the solution instead of ammonium, because you don't have any positive charges floating around and any positive charges get quenched immediately. But that's essentially the only major difference.